Hello and welcome to this video of Easy IGCSE Physics, and I am Shimantak. Today we are going to look at moments, center of mass, and equilibrium. Moment is defined as a turning effect caused by a force about a pivot, and its magnitude is force times perpendicular distance. This is the symbol for perpendicular if you need to use it in like further physics or maths. A force on an object would either cause the object to rotate clockwise or anti-clockwise. Now, from this formula, moment is directly related to perpendicular distance from pivot if force is kept constant. So, if we want to produce the same moment or the same turning effect, we can do it at a much lower force if the distance from the perpendicular distance from the pivot is increased. This is basically what it says here. An example would be opening a door. It is much easier to open the door if the force is applied far from the hinge in comparison to applying the force right next to the hinge. The hinge basically acts as the pivot here. Now let's look at equilibrium. In physics, there are two types of equilibrium. Translational equilibrium, and this is the one that you have normally heard about, which is basically the net force acting on the system is equal to zero. And the effect of this is that the object moves at a constant speed in a straight line or at rest. This is basically it's basically hinting at Newton's first law. But the second one is rotational equilibrium. This is when the net moment acting on the system is equal to zero. Effect, the object does not rotate in any direction. And therefore comes the principle of moments, a very important equation, I would say, for questions in IGCSE physics related to moments, and that is total clockwise moment equals the total anti-clockwise moment. Now let's look at center of gravity. It is an imaginary point through which the weight of an object is assumed to act. And for an object with uniform density throughout, the center of gravity is the point where all the lines of symmetry of the object intersect. So for this object with a shape like a rhombus, it has two lines of symmetry which intersects at this point, and therefore, if it has uniform density throughout, that is the center of gravity. Now, what does the center of gravity actually mean, and why did it, like it's an imaginary point, so why did it come into existence in the mind of scientists? Let's see. Consider a rod. Consider the rod to be made of infinite number of point masses. Each point mass will have its own weight, and this weight all acts downwards. Now, if you consider the mass, the rod to be having uniform density, then at the center of the rod, there is this point where the total clockwise moment, which comes from the right direction, equals the total anti-clockwise moment, which comes from the left direction. So if you consider that point as a pivot, then the net moment is equal to zero. So the rod is at rest. And if you consider that point as pivot and all the force of gravity to act from that point, then you are basically doing a vector summation of all the forces of gravity on the point masses, and therefore you get a much larger net force of gravity acting from the center of gravity. Now, center of mass is often related to stability. An object is stable as center of gravity lies above its base. The base is basically this. An object would not be stable if, due to a turning effect, the center of gravity does not lie above the base anymore. If this happens, the object will topple over now, as the force of gravity will create a large enough resultant moment. This is very important. It's not because that the reason of physics behind why it will topple over is the moment that will be created by the force. Now, you see an object with a tall base, with a narrow base and a high point, which is the center of gravity. And this is an object with a wider base and a much lower center of gravity. For this object to topple over, you need to rotate it by a much larger degree. So, this means that objects with wide bases and low center of masses are more stable than those with high center of mass slash gravity and narrow bases. A real life application of this would be when trucks and buses are advised to be careful on very windy days, as their high center of gravity and relatively narrow base makes them easy to topple over than other vehicles like cars. Now we are going to look at two pretty challenging questions related to moments. The first of which is this. A 20-meter long uniform bridge of weight 100 kilonewtons is supported at each end by pillars as shown. This is basically the diagram. The pillar exerts force T1 and T2 on the ends of the bridge. What are the values of T1 and T2 when a van of weight 24 kilonewton is on the bridge 5 meter from the left-hand pillar? Let's, most of the information is given, but one piece is not. 5 meter from the left-hand pillar in the diagram. So I would write that down. Okay. Now, the strategy in solving such questions is consider one of the pillars as a pivot. Say I consider this part, the left pillar, as a pivot. Then this van and the weight of the bridge acts as clockwise moments. So clockwise moment, I'm going to just write C equals, sorry, I'm just going to write it more clearly. C equals, the moment here would be 24 kilonewtons times 5 meters plus 100 kilonewtons, which is the weight of the bridge, times 10 meters. The reason why I'm saying 10 meters, if it's not explicitly stated, we assume that the object we are looking at has uniform density. And if it has uniform density, it will lie along the line of symmetry, which would be at the exact center of the object. And the length is 20 meters, so center would be 10 meters. So if you calculate this, this would be 120 kilonewton meters, and this would be 1000 kilonewton meters. So it would be, if you add 1000 and 120, 1120 kilonewton meters. Now, this is the total anti-clockwise moment. Sorry, total clockwise moment. My fault. You see, it's pretty complicated. The clockwise, anti-clockwise, it gets mixed up in the head. So we have to be pretty careful. Now, T2 produces an anti-clockwise movement, and the bridge is not collapsing or anything. So basically, the system is in rotational equilibrium, which means we can apply the principle of moments. The total clockwise moment equals the total anti-clockwise moment. So AC, anti-clockwise moment, equals also 1120 kilonewton meters. and this is equal to the force of T2. So I'm just going to write T2 times the distance from T1, which is 20 meters. So T2 is 1120 by 20, and kilonewton meter by meter becomes kilonewtons. And this is 56 kilonewtons. Now, if I was in a real MCQ exam, I would directly pick C because T2 has 56, there's only one option. The other options are 68, 62, and 50. But I would like to explain a way of actually finding out T1 if, say, there were 2 or 3 options that had 56 for T2. How? Let's discuss. Well, there would be the hard way of finding the moment of T1, considering T2 as a pivot, and then calculating the force by dividing it by the distance of 20 meters. But there's a much easier way. There's also translational equilibrium. The whole system is not moving towards any direction or anything. It's not accelerating. So if there's translational equilibrium, total force downwards, F down, I'm just going to write it like this, equals F up. So the net vertical force equals 0. F down is basically weight of the van plus weight of the bridge, which is 124 kilonewtons. And weight up equals T1 plus T2. Now we just found out T2, which is 56. So T1 equals 124 kilonewtons minus 56 kilonewtons, which would give us 68 kilonewtons. And there's our answer. So even if there were multiple options with 56 as T2, you could find it out pretty easily after you had found out T2. So finding out one of them is basically the hard part. Then it becomes easy if you know how to apply the small trick of applying translational equilibrium instead of rotational one. Yet again. Now, this question is one that I really like because it does not use any complicated maths or anything, but it really tests on the concept very deeply. So let's solve. The diagram shows the minimum force F1. I'm just going to highlight it. Acting on a lever required to lift a heavy log of weight W. Log of weight W. Let's highlight that whole system. The log needs to be lifted by a smaller force than F1. The diagram shows the changes tried. Each diagram has only one change from the original diagram. In each case, F2 is a minimum force required to lift the log. And this is the pivot. These are the 3 changes, P, Q, and R. Immediately, I know these are the changes, so you should circle, highlight whatever you want to do. In which situations will F2 be smaller than F1? Okay, situation P. Increasing the length of the lever to the right of the pivot. So we are increasing the perpendicular distance. Now we need the same turning effect, so the same moment. I'm going to write moment as M, capital. And if I increase D, it's the product of force times perpendicular distance. I can basically decrease my F, because if you increase both, the total moment is going to increase, which we don't need to do. We just need to keep it same. So by increasing the length of the lever to the right of the pivot, we're increasing the moment caused by F2. We are not in, sorry, my fault. See how it's easy to go wrong with this. We're keeping the same moment caused by the force by decreasing the force. So F2 is indeed smaller than F1. So P is a tick. Now let's consider Q. Applying the force perpendicular to the lever. I will go back to this part because it's easier to demonstrate here. In this case, there's one important thing when we need to consider about the moments. It's that the force acting on the object must be perpendicular to the system. So it's this, sorry, this actually destroys the whole aim, which is to show that F2 is smaller than F1. So this is effective force, F effective. I'm just going to write FE. If you consider this to be a right angle triangle, F1 is the hypotenuse, so FE is smaller than F1. So only a perpendicular force of FE is required to make the object rotate by this amount. So as FE is smaller than F1, the perpendicular force in this case is F2, and the smallest value F2 can take is FE. So replacing F2, FE with F2, F2 is smaller than F1. So that's yet another tick. The last one, R, increasing the distance from the log to the pivot. When you're doing this, you're increasing the anti-clockwise moment. So a larger clockwise moment is needed to cause the object to rotate. And as the distance between pivot and F2 stays the same in comparison to this situation, the moment would increase only when the force is increased. So F2 is a larger force than F1 in this case. So R is a cross. So P and Q are the two ones at work, and therefore the correct answer is option B. As you could see in this question, it was a lot of step-by-step process, and in an actual MCQ exam, spending this much time on two questions is not advisable. So either I would say skip the question and come back at the end, or try to do some parts in the head. So you don't need to write down this. You can do this in the head or directly in the calculator. Or as you can see, I wrote down all of this. Probably I would only recommend to write the one about Q because it's a bit complicated, but P and R you can do with basic knowledge of moments in your head. Okay, this is the end of the video. Thanks for watching.